Okay, so we are in section 2 of chapter 7. And chapter 7 has some really interesting applications, especially for those, you're going into some type of STEM major, science, tech, engineering, or if I can convince you, maybe even mathematics, right? But the good news about chapter 7 is we finally get to see some applications, right? Some real world type applications uh, where you would use some of this calculus, okay? So what we're going to do is we're going to start with a technique for finding volumes. Now, volumes meaning we are leaving the two dimension, the comforts of two dimensions, and we seek information about a three-dimensional world, right? The volume of something. Now, in this particular method, we're looking for the volumes of what we call solids of revolution. Now, to give you a few ideas of what do you consider a solid of a revolution? Well, axles or funnels or pills or bottles or pistons. All of these are what we call solids of revolution. And all of them, you can find the volume of all of them using a method called the disk method, right? So this is the disk method. Let me do my best to try to explain what's happening here. So let's start with this little rectangle that we have here. Okay, so this rectangle obviously has some width, it has some height, right? So it would be really easy to find the area of that rectangle. Now, what I need you to imagine for a second, and on the next page I'll have a better picture of this, but I need you to imagine that this rectangle is going to rotate, right? It's going to rotate about this line of y equals x. So you can imagine that it's rotating all the way around till it gets right back to where it started. If you don't mind, let me see if I can come back to the page I'm on, but let me go to the next page. So again, you have to imagine you have this rectangle here is rotating. And as it rotates, you can see that it's tracing out some type of, you could, if it were a single line, it would trace out a circle, right? Kind of like what you can see here. But obviously, since it was a rectangle, it's going to trace out some type of disk. Let me get back to where I was. All right, now, so far so good. So take a look at this curve. Now, imagine if this, instead of just rotating that one single rectangle, imagine if you rotated that whole curve. Please stay with me, because I lose so many students when we get to chapter 7, and it's a shame because this is where you get to see this stuff in action. So bear with me, please. Let me have your attention. So if you will agree with me that this one rectangle, when you rotate it through the x-axis, that will create one disk. Now, then let's see if we can understand this idea of the radius. Well, of course, a circle has a radius, right? A radius r. And can you see how the radius of that disk translates into the height of this rectangle? Do you agree? And can you also agree with me that the height at each of these points varies? So the height at the first point here is larger than the height at the second point, which is larger than the height at the third point. And so what that would mean is once it rotates, that would mean the radius of this particular circle would be larger than the radius of this circle, which would be larger than the radius of this circle. So can you agree with me that the radius is going to vary along this curve? Okay. Well, let's start with just forget about calculus for just a second. Let's start with just the volume of a disk, right? If this were back in geometry class and I just gave you some type of disk, and let's just assume that I gave you the width and I gave you the radius, then you can find the volume of that disk by simply using the following formula, right? So pi multiplied by the radius squared multiplied by the width would give you the volume of this single disk. Now, what we're going to do is, instead of using the term W for width, right, and notice that in this case, the width of this rectangle, we're going to go back to our notation of delta x, right? So delta x is just the width of this rectangle. So if we're going to let W be represented by delta x, you can see how I've substituted delta x in here. Now, why? So next, let's look at the left side. So this is the volume of a single disk, but you just got done agreeing with me that the volume, if the radius changes, right, the radius of this circle would be larger than the radius of this circle. If the radius changes, then the volume would change. So the change in volume is what we're using here, can be calculated by the following formula. So, all right, and now how do we get from here to calculus? Well, look, if I integrate both sides of this equation, well, I would actually arrive at the total volume, right? Because remember, this whole thing, you can imagine this entire thing is going to, it's composed of an infinite amount of disks, and we want to find the volume of the whole solid. So the volume of the entire solid can be found by simply integrating. Now, if we're going to integrate, we need to have a place where we start and where we stop, right? So this, if you think about it, this graph starts at A and this graph stops at B. So from A to B. And then what's left is pi r squared. Now that r, I'm going to, instead of just writing r, I'm going to write as r of x. That's the radius, because why? Because how would I know the radius at this point here? It would depend on the x value. And what about the radius at this point? It would depend on the x value. So radius is a function of x. And finally, if you're going to integrate x with r of x, it needs to be with respect to x. So that's the idea. That's the idea without my software. I don't have access to my software, but that's the idea, spatially at least, of what's happening, right? So we are going to end up finding the volume of a solid. And the idea is, starting off with just say one disk, we let the number of disks approach infinity, right? Obviously, as the number of disks increase, the number of rectangles, or at least the width of each rectangle, decreases. Okay, so we now have our formulas. And notice that we have two formulas for the disk method for horizontal axis of revolution and vertical axis of revolution. It's fairly positive. If you notice, you have the same curve here, but if it depends if you're rotating about the horizontal axis or are you rotating about the vertical axis, right? So is this line rotating about the vertical or the horizontal? And the only difference, the main difference is if you're rotating about the horizontal axis, notice that you are integrating with respect to x. If you're rotating about the vertical axis, you're integrating with respect to y. All they did was, since pi is a constant, they just brought it out in front of the integral. Let's jump right in. So we want to use the disk method to find the volume of the solid formed by revolving the region bounded by the graph of f of x is equal to the square root of sine of x and the x-axis from 0 to pi. And here's the key part. We want to rotate about the x-axis. Okay, so as soon as you read about the x-axis, that narrows down our two formulas. We know that we're dealing with the horizontal axis of revolution. Okay? All right, so let's go ahead and write our formula. So we got the volume is going to be equal to pi, and we'll fill in the rest in just a second. So we're going to be a little bit spoiled here because I already have the geometry of what this looks like. In fact, I even have the result of what this looks like, right? So if you're trying to 3D print some footballs, maybe you're in some type of CAD program or something to this nature, and you're trying to 3D print some footballs. So notice that this is not a bad little equation, the square root of sine of x, to use so that when it rotates, you get a football. Make sense? Now, our job is to find the volume of this football. Okay. So let me kind of give myself some space here. So in this case, r of x, so r of x, that's the radius function. That's just simply equal to the square root of sine of x. So that's not bad. All we're going to do is substitute the square root of sine of x in for r of x. All right, so we need to go from a to b of r of x squared and integrate with respect to x. Okay, so we know what we're plugging in here and then squaring it. Now, we also need to know, where do I start, where do I stop? All right. Well, the good news is that is all specified here. Notice that you're starting at x is 0. You are stopping when x is equal to pi. You can imagine there's a vertical line here at 0. There's a vertical line here at pi, and you're rotating about the x-axis. So see how I've for lack of a better word, boxed in. I've trapped in this little this curve so that it's bounded and I can find the volume. Okay, without that, if then I might end up with an infinite volume. All right, so let's substitute everything in. So we're going from 0 to pi. So from 0 to pi, and we're also plugging in sine of x, and then we're not forgetting to square it, okay? So that's going to be pi, 0 to pi, square root of sine of x squared dx. I do need to see this work, and I do need exact solutions, right? So you can't just give me some decimal approximation of this volume. That's nice. That's just not very interesting at your level of mathematics. So let's go ahead and square. Well, if you square a square root, you're just going to be left with sine of x, right? So pi 0 to pi sine of x dx. Well, this is a fairly easy integration. If you integrate sine, you just get negative cosine. So that's pi negative cosine of x. And now all we need to do is we need to use that first fundamental theorem of calculus, right? That's so the f of b minus f of a. So what we're doing here is, so we're going to be plugging pi in for x. That's negative cosine pi minus negative cosine of 0. So let's finish that up. So that's pi times. Alrighty, so this is going to be negative cosine of pi. Just so you understand, that's f of b. Minus what? Minus negative cosine of 0. Again, that is f of a. Okay, so let's just clean this up. So we have cosine of pi is negative 1. So that we end up with negative 1. Cosine of 0 is 1. So that's minus negative 1. So as you can see, we have double negative. We end up with just pi times 2, or 2 pi. So that's the volume. I don't know what type of units we're measuring in, but that is the volume of that football. Okay. So we're going to do one more, and then we're going to take a break. And the next one is going to be fairly similar in that it's going to be horizontal axis revolution, except imagine for a second, imagine if I took this this curve, and instead of it starting here, what if it was up here? And one more thing, what if instead of revolving about the x-axis, what if I revolved about some other axis? Well, let's see if you can, let me get to the problem and see what I'm talking about. All right, as I'm drinking coffee. All right, ready? So we want to find the volume of the solid formed by revolving the region bounded by the graphs. So here's our first graph, 2 minus x squared. And we have another graph, g of x equals 1. And here's the part where I need you to slow down. I need you to take some notes. About the line y equals 1. All right, so again, we're going to jump to the geometry, but this geometry won't be there waiting for you on the test. So draw it, right, or graph it. Take a look at the geometry before you start doing some jumping into the equations. So here's the graph of 2 minus x squared. Okay. And notice, so I'm going to start to write. I'm going to write some information here, right? So I'm taking notes. So this is f of x is equal to 2 minus x squared. Now, obviously this parabola continues onward, right? So we have to bound that if we want to be able to find a volume. So notice that g of x equals 1. So we got g of x is equal to 1. So what does the geometry, so if the geometry of 2 minus x squared, if that's this parabola, what is the geometry of g of x equals 1? Well, that's just like a horizontal line, right? That's just the horizontal line y equals 1. So that's this. Now, here we go. What do we want to revolve about? We want to revolve about the line y equals 1. So here is the line y equals 1. Right, here's the x-axis down here. So, but we want this curve, right? We want this curve to revolve around this line. Not this line. Or not the x-axis, around y equals 1. Well, either way, whether it's this blue line or the x-axis, it's still horizontal revolution, right? It's still going to be the horizontal formula. So we're going to be using our horizontal axis of revolution. I'm going to go ahead and start writing that, and let's see what other problems we might run into. So the volume is going to be equal to pi, and we're going to integrate from a to b of r of x squared dx. And here we go. So these types of problems, they really do get a lot of students. If you've taken some of you, this may be your second time taking Calc 2, and that's okay. And maybe you can even remember problems like this really tricking you. So listen to me. The way you got to think about this. So the first thing we're going to need to figure out is what is r of x, right? The prototypical Calc 2 mistake is a student just grabs whatever f is and they plug it in, right? That so happened to work on the previous example. That's not the way you want to think about these problems. So let me see if I can make a statement here. Remember, we are revolving around about this blue line. Look, if we were just revolving about the x-axis, right? If we were revolving about the x-axis like the previous example, then you would be good to go just taking f of x and plugging it in. But we're not. We're not revolving about the x-axis. We're revolving about y equals 1. So what you will need to understand is you're going to end up subtracting these two in order to figure out. But you could be adding, right, depending on the problem. So I'll try to unpack that. In this case, it's going to be f of x minus g of x. Let me write that out. And then I'll see if I can unpack why we're subtracting g of x instead of adding. So first off, f of x, that's just 2 minus x squared. And of course, g of x is simply equal to 1. Now why, here's the question, stay with me, why minus g of x? Well, do you agree with me that, just take this point right here. So this is when y equals 1. If you were to subtract 1, do you see how you would get that point right back down to the x-axis? Do you see how if you just subtract 1 from every point on this graph, you would literally be adjusting it so that it would be rotating about the x-axis. That's why you're subtracting 1. If this curve were below the x-axis, how would you get it back to starting position? You would have to add 1. That's the best I can do using informal language to help you out. So let's go ahead and finish up. So now that I know r of x is just, in this case, f of x minus g of x, that's just going to be 1. So I got 2 minus 1. So that's just 1 minus x squared. Okay, so beautiful. So that is what we're going to end up plugging in for r of x. But what about this? How do we find these bounds? Well, will you agree with me that the graph starts and stops at the points I'm highlighting? And will you agree with me that this particular point right here is the intersection between this graph and this graph? They intersected this. So in other words, I need to find the points of intersection, right? So let me so to find A and B, we need the points of intersection. All right. So that's easy. You remember, if you have to find the points of intersection, we can just take our two graphs and set them equal to each other. So we can just take f of x, set that equal to g of x, and then we can solve for x. So that would be 2 minus x squared is equal to 1. And now you just solve for x, right? So subtract 2, and then we'll end up dividing by a negative, and then we'll take the square root. So x is equal to plus or minus 1, right? You know, you're with me. Minus 2 both sides. That's just negative x. After you do that, it's negative x squared equals 1 minus 2 is negative 1. Divide by negative 1, divide by negative 1. At that point, it's just x. Let me write. At that point, it's just positive x squared equals 1. Take the square root of both sides. X is equal to plus or minus the square root of 1. And the square root of 1 is just 1. So that's how we get plus or minus 1. So there it is. So this is A and B. All right, let's go ahead and rewrite our volume formula. So volume is equal to pi. We want to integrate. Now, if we're going from negative 1 to positive 1, right? So A is where the starting. So we're starting at negative 1. And we're proceeding to positive 1. All right, and what did we figure out r of x is equal to? Well, r of x is equal to 1 minus x squared. Okay. So look, I mean, at this stage, I'm not trying to trick you a lot with the integration, right? I'm not trying to throw extremely hard integration problems at you. So and you can just FOIL that out to make the integration easier. So I'm going to write that here, but then I'm going to erase it. So 1 minus x squared, we can just FOIL that out. That's just 1 minus x squared times 1 minus x squared, okay? So that ends up being, the volume is pi, my apologies. So the volume is pi integral negative 1 to 1. So this ends up being 1 minus 2x squared plus x to the power of 4. All right, so if you FOIL that out, that's what you would get. So 1 minus 2x squared plus x to the power of 4 dx. See what I'm doing? I'm just foiling to make this, because once I FOIL this integrand, this is a really easy integrand to, a real easy integration. Okay, so let's go ahead and integrate this. So pi, so if you integrate 1 with respect to x, that's just x, right? Because the derivative of x is 1. Then we integrate negative 2x squared, so that's minus 2x cubed over 3 plus x to the 5th over 5. And don't forget to negative 1 to positive 1. So that last step is going to be f of b minus f of a. So that's f of 1 minus f of negative 1. Okay, a lot of work. If you give me a decimal, I take off points, right? Massive amount of points, depending on if you just give me an answer, I give you 0 points. I need to see all this work, but the result is 16 pi over 15. That's a lot of work, or a lot to digest for one video. So let's go ahead and stop here, and I'll see you in part B.